Alright, friends, how are we doing? So, we've got our first lesson on probability. Yay! One of my favorite units that we have in here, if not my favorite. So our goal today is to be able to define probabilities and different types of probabilities, and then also to be able to conduct simulations in order for us to predict probabilities. So here's the scenario we are looking at. So there was an old game show called Let's Make a Deal. I believe they've brought it back, but it was originally an older game show. In that, there would oftentimes be 3 doors. Behind one of the doors would be a fancy new car. Everybody wants the car. And behind 2 other doors, there are some goats or some joke prizes. Again, we're going to call them goats. Now, suppose you pick door number 1. Now, the host, he actually knows what prize is behind each doors. And he shows you, opens the door, one of the doors that has the goat. Right? Again, he knows where everything is. He opens one of the goat doors. And then he says, do you want to stay with door 1 or do you want to switch? So if you were chosen in this game show, which do you think would be the best strategy? To stay, to switch, or does it not matter? Take a moment and think about that. Alright, so in order to kind of, maybe we don't know the probability of staying or switching and seeing that. So oftentimes when we're faced with a problem like this where we're not exactly sure how the probabilities are going to work, we run something called a simulation. And what a simulation is some sort of model that imitates chance behavior. Okay. And on Schoology you'll see an applet that can kind of allow you to play around with that. Now, obviously, we're not in class together, so I'm going to use some data that I collected from one of my previous classes, and we found that if students stayed in 3 of the scenarios, they would have won. If they had switched, they would have won in 5 scenarios. So staying and winning, there was a 3 in 8 chance of that occurring. If they switched, there was a 5 in 8 scenario. Interesting. You can see perhaps a little trend here. This is a fairly small sample size. We'd want a larger one than this. But maybe we can start to see that switching and winning might be a better option. Well, let's look at a theoretical probability. Let's look at all the possible scenarios we could have and find a theoretical probability. So down here we have our there we go. We have our sample space. Let me zoom this out just so I don't miss anything. Okay. Right here, this is our sample space. Now what is a sample space? Well, that's just a list of all possible outcomes of a statistical experiment. Alright, so here are all the possible scenarios. Now again, in our scenario we are choosing door 1, but it wouldn't matter if we choose door 1, door 2, or door 3. To start with, the scenarios are going to be the same. Right? So we know that there's 1 car and 2 goats. So if I choose door 1, what are the possible outcomes? Well, the car could be behind door 1. If the car was behind door 1 and I chose door 1 to begin with, I would win. And if I switched, I would lose. Okay. The next possible scenario is I choose door 1, and the car is actually behind door 2. Now, if I choose door 1 and I stay with door 1, I would lose, right? There's a goat there. Right? Now, again, our buddy Monty Hall, who is the host of this show, has to show us door number 3, right? Because he has to show us a goat. And so the only door I could switch to was door 2, in which case I would win. Right? The third possible scenario is that the car was actually behind door number 3. I choose door number 1. Monty Hall has to show me door number 2. Right? If I stay with my door, then whoops, I get a goat. I lose. But if I switch, the only door I can switch to is door number 3, and in this case I win. Interesting. So again, these are the 3 possible scenarios. It would be the same as if I chose door 2 or if I chose door 3. We would still have 3 possible scenarios of where the car could be. It could be behind door 1, door 2, or door 3. And we notice, I'm going to go the theoretical probability first. We notice that in only one of my 3 possible scenarios will I win if I stay. Whereas if I switch, there are 2 wins out of 3 possible scenarios. So actually switching is a better strategy, and it's not 50-50. It's actually 66% chance, 2/3, 66, 67% chance of winning. Okay? A 2/3 chance of winning if I switch the door. The experimental probability, well, that would be the probability from our simulation. Okay. We found in the simulation that I ran with one of my other classes that 3 out of the 8 stayed in 1, and 5 out of the 8 switched in 1. So what is an experimental probability? Well, an experimental probability is a probability calculated based on the results of a simulation or experiment. Okay. Now, we notice that our experimental and our theoretical probability aren't quite the same. So why aren't they the same? Take a moment and think about that. So maybe you thought, oh, well, the number of trials doesn't even allow them to be the same, right? This isn't divisible by 3, so there's no possible way. Well, it's kind of the right idea. The theoretical probability does have to do with trials. Is the result that we would expect to see if we ran many, many trials. So that's kind of what a theoretical probability means, and it's a really important concept. Right? If I run 1 or 2 trials, then perhaps my results will be wildly different than my theoretical probability. But if I run thousands and thousands and millions and millions and millions of trials, then we're going to expect those results to be very close to theoretical probability. Really, really important concept here that we're going to discuss a little bit further as we go through these notes. Taking a look at the back. So what are random phenomena? Well, random phenomena is a situation whose outcome we cannot predict in the short run, right, with a few trials, but there is a pattern to its distribution when there are many trials. Right? Flipping a coin, you can't predict if it's a heads or a tails in the short run, but we can predict the distribution after many, many, many trials. Okay. So when conducting a simulation, we saw that with a small number of trials, so when you were running your applet, you would see that it swung from like 100% to 100% to maybe 50%, right? It swings wildly. There's a lot of fluctuation. But when we conduct, or if we conducted thousands of trials, many, many trials, then we would get closer to our 2/3. Right? And that's something that we call the law of large numbers. This is really, really important. This is kind of the definition of our theoretical probability, or it really, really feeds into that theoretical probability. So, the law of large numbers says that the proportion of times an event occurs after a large number of trials approaches some value. So after many, 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 many trials, we would be able to predict what's the probability of something occurring. Okay? That proportion is the theoretical probability. Again, the theoretical probability is the proportion of times that that event occurs with many, many, many trials. Thousands, millions of trials. Right, with that in mind, take a moment and think about what these three scenarios really mean. So what does the probability of rolling a dice and getting a 3 really mean? Well, it means if I roll dice many, many times, a 3 would occur about 1/6 of the time. Right. Got to put both of the menus in there. Not actually, but it is lots and lots of trials. That's kind of what we're trying to emphasize here. If I pick a work day at random, the probability that it will be a Monday is 20% or 0.2. Okay. And again, what would that mean? What does that actually mean? After randomly. That's important. Picking a work day many times, or many, many times. In proportion of Mondays chosen is 0.2. Right? About 1/5 of those days should be Monday. The last one's a little bit harder to think through. What does it mean when a weatherman says, hey, there's a 70% chance of rain today? Well, in this case, you see that after looking at all the days with similar conditions, it rained on 70% of those days. So that's what weathermen are looking at. Okay, based on these conditions, how many days did it rain on those, or how many times did it rain on those days? Well, about 70% of those days it got rain. Pretty cool. So let's take a look at our first kind of myth that a lot of people think about. So which of these following outcomes is more possible? Now in this case, the order is going to matter, so I flip a heads first, flip a heads second, heads third, heads fourth, then a tails, then a heads. Would that be more likely? Or would a heads, then a tails, then a heads, then a tails, then a heads be more likely? Well, think about it for a second. All right, and then keep in mind that assuming that we have a fair coin, there's a 50-50 chance of each of these occurring, right? So the probability of the first would be 0.5 to the power of 1, 2, 3, 4, 5, 6 to the power of 6. I'd just be multiplying those together. And how about here? Oh, it's the same thing, right? In that order, these two outcomes have the same probability. Okay, what about if I flip a coin 10 times and I get a heads, then a tails, then a heads, then a tails, 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 then a tails. I think I got that number right. What do you think they'll get on the next flip? The next flip. Well, in this case, it's still a 50-50 chance. Doesn't matter that I flip so many heads in a row, right? The probability of the next event occurring does not change based on a streak. So that's a concept that is used a lot when dealing with dice or dealing with chance probability. Oh, I've gotten so many, that means that a heads has to come next. No, it's still a 50-50 chance. The previous outcome does not affect any future or affect the current one. At least not in this scenario. So those are some of the common myths. All right. So, in case you still don't believe that switching was the best strategy, what if we did it with 50 doors, right? So, when you first chose it, you had a 1 in 50 chance of choosing the car. Then Monty Hall shows you all of the 48 goats, and you could stay with your door, which had a 1 in 50 chance of having the car, or you could switch to the other one. Well, remember, in this scenario, it was only a 1 in 50 chance. So there was a 49 out of 50 chance, right, that the car was not at your door. And again, Monty Hall has shown you all of the goats. Switching is definitely going to be better in this case. And I realized I wasn't showing you the right part of the notes. Sorry about that. Now, one of the things that you're going to have to be able to do for the AP exam, for my test, is write up how to run a simulation. Okay? What if I don't know the probability of something occurring? How could I simulate it? Right? And a lot of times we do this. Statisticians will do this for very difficult probabilities, or if there are a lot of unknowns or something like that. So really important to be able to write and create good simulations. So we're going to start with our state, and the state's going to be, so we're going to do our 4-step process just like before. So our state is just going to be stating what we're looking for. It can be a sentence. Right. Then for our plan, we're going to identify all of our possible outcomes. Okay, we're going to identify the probability of each outcome. Then we're going to assign some chance device. Could be dice, could be a coin, could be a random number table, could be our random number generator on our calculator. Then we're going to explain, this is an important one that people forget. Explain what we record. Right? What data am I collecting here? Right? For the do, we actually perform the trial. And then for our conclude, we're going to use the result to answer the question. Right. So let's take a look at our first scenario together. Right, we're at a local high school. 95 students have permission to park on campus. Each month, the student council holds a golden ticket parking lottery at the school assembly. 2 lucky winners are given reserved parking spots next to the school's main entrance. Last month, the winning tickets were drawn by student council members from the AP Statistics class, so only AP Stat students. When both golden tickets went to members of the same class, some people thought that the lottery had been rigged. There are 28 students in the AP Stats class, all of whom are eligible to park on campus. Design and carry out a simulation to decide whether the lottery was rigged. So what are we trying to figure out in this scenario? Well, we're trying to figure out What is the probability that both spots go to AP Stats students? So for our plan, what are the possible outcomes? Well, what are the things that we care about? We care about the student is in the class, right? Or the student is not in the class, right? So again, we have 95 total students, 95 total students, and 28 of them are in the class. So let's let (0, 1) to 28, since we're going to be using a random number table here, represent students in the class. Okay. And then 29 to 95 represent students not in the class. Now, how would we use a random number table to run this simulation? So we would close our eyes and point to a random spot. On the random number table. From there, what would we do? We would go across 2 digits at a time until, and I'll actually spell it right this time, we choose two numbers between 0, 1 and 95. Now in this case, I forgot to write unique, so I would just write skipping repeats, because I can't choose the same student more than once. Right? And then the last thing, don't forget this, the last thing we need to talk about is what do we record? But what do we care about? All we care about is whether or not the 2 students were in the same class. So we record whether both numbers are between 0, 1 and 28. Okay. Now a lot of times 50 repetition is what we want. So in this case we will do, we're only going to do 30. And again, I'm just going to record yes or no. Okay, so let's start, we have 55 and 58, and I like putting kind of a little bar here to represent, hey, I've finished one trial. So this is a no. Not both students are between 0, 1 and 28. 89 and 94. That would be a no. So that's trial 1, trial 2. Okay. 04 and 70. Not both are in the same class. We've got one in the same class, but no. Now in this case, 70 is okay again because it's a new trial. 70 and 84. That's a no. 10, 98 is outside of our range, so we can cross that out. 10 and 43. That's a no. So I have 5 no's so far. 56 and 35. That's a no. 69 and 34. That's a no. 48 and 39. That's a no. 45 and 17. That's a no. 19 and 12. There's our first yes. 97, we can't use that, right, because we're only going up to 95. So 51 and 32, also a no. And I'm going to do 15 to spare you from listening to me throughout this whole thing. 58 and 13, that's a no. 4 and 84, remember they both have to be within that range, so no. 51 and 44, also a no. 72 and 32, also a no. And just for fun, just to get another one in there, 18 and 19, that's a yes, that's a yes. Right? And then you continue working on going through this random number table to collect the rest of your data. Now for me, I'm going to stop here because again, you don't want to hear me saying no or yes. Hopefully you get the process. Okay? So our last thing that we need to do is conclude. Last thing we need to do here is conclude. So in our case, we had 2 in 16 chance. Now you can write your answer as a decimal, as a percent, or as a fraction. Any of those are fine. I would say according to the simulation, and this is 216, there is a 0.125 chance. Both students are 12.5% if you wanted to write it that way. Are from the same AP Stat class. Right, and that's it. That's how we would conclude. We use the percentage or the fraction from up here. Right, fraction works. We would want to say according to the simulation. Right, and that's how you run a simulation. On the back here, you have a simulation you can run. I'm going to post the key for that, but let you work on this one on your own. Okay. Good luck. Have fun.